It's been a while, hasn't it? And I apologise. I spent the last few weeks smashing out hundreds of videos for the AI Tutor GCSE course. And it's shaping up nicely, but found a bit of time, it's a Monday morning, we'll loop back to the YouTube for a bit. So what I wanted to do was another past paper, and I really wanted to make sure it was a year 12 one, because they're just so useful. Obviously for year 12s, but also for year 13s. Like if I'm tutoring a year 13, just starting off, I'm like, look, do a year 12 paper. There is no point in messing about with your parametric differentiation and all of that stuff if your base, if your core year 12 knowledge is not on point. So we'll do that first, make sure everything is there, and then once we're confident with it, we'll move on to the year 13 stuff. So I've got an Edexcel paper. It's going to be June 2018 paper 1. So this is pure mathematics. Let's give it a crack. So question 1, so it's an integral in it. So find the integral of all of that stuff, giving you answer in its simplest form. So this is a really great way for the examiners to test your integration, but also your indices. Because look at this second term, they love doing this, right? I'm just going to write the 2/3 x cubed here, nothing needs to change to that. They want you to notice that the way we integrate polynomials, or like powers of x, is by adding 1 to the power and dividing by the new power. We've got a square root of x here, so they would really like it if we were to express this square root of x as a power of x, because then we can say, oh yeah, this is how I integrate it. So what is the square root as a power? It's the power of a half. So instead, you're going to want to write the following, minus 6x to the half. And then you're in a better spot. Because now, I basically just integrate by adding 1 to the power and divided by the new power. So here, I'm going to get what? I'm going to get 2/3, because that just chills out front. And then x cubed, so add 1 to the power to get x to the 4, and then divide by the new power. So divide by 4, or multiply by a quarter. And then minus 6. Add 1 to the power of x. So a half add 1 is 3/2. And then I need to divide by 3/2, which is the same as timesing by 2/3. And then 1 is essentially x to the power of 0. So imagine I had x to the 0. Add 1 to the power, I'm going to get x to the 1. Divide by the new power, divide by 1, right? So it's basically going to be x. So this is just going to be plus x. Is that it? Of course, it's not it. We need a plus c. If any of you in your exam don't write a plus c when you need to, I'm going to disown you, because you shouldn't be doing it. It's unacceptable. Write your plus c. So giving you answer in its simplest form, we're probably going to want to clear this up a bit, aren't we? So let's have a look at these fractions here. I think I can cancel a 2 here. Because I have a 2 divided that by 4, so that's the same as basically having 1 divided by 2. So this would almost be 1. And then I would get what, like 3 times 2 on the bottom, which would be 6. And then x to the 4. Minus. Well, 6 and 3 cancel really nicely, don't they? 6 divided by 3 is 2. So I've got 2 times another 2. So that's going to be minus 4x to the 3/2. Can't do anything to the x. Can't do anything to the c. So I think we're sorted for question 1. Question 2. Show that x squared minus 8x plus 17 is greater than 0 for all real values of x. It's just always completing the square. Like, it's always completing the square. If you want to show an inequality, like a quadratic one, basically, if you get everything onto one side, and you get, like, square number, then you know that square numbers are greater than 0, or greater than or equal to 0. That's usually what you want to do when you're proving inequalities. So even if you have an inequality where it's like something on the left and something on the right, what I would generally suggest is get it all over to one side and try and get a square number or something. So, look, have a look at this. Complete the square on this, okay? So it's going to be what? X minus 4 squared minus the 4 squared, so minus 16, plus the 17. Okay, so I'm not going to write greater than 0 here, because that's what I'm trying to show, isn't it? So I'm not just going to assume the result, I want to show it. So cleaning this up, I'm going to get x minus 4 squared plus 1, right? Now, this is made up of 2 parts. The first part would be the 1, let's call that part 1. And then the second part would be the x minus 4 squared. First part is always 1, isn't it, right? Like, no matter what the value of x is, 1 is always equal to 1. It's a constant. So this thing here, always equal to 1. This thing here, I don't care what's inside this bracket. But what I care about is the fact that whatever is inside this bracket is then squared. So can this bracket, once I square it, can it ever be negative? No. Like, imagine the thing inside the bracket was minus 1 billion. Once I square it, it's going to become positive, right? If it's positive 1 billion, once I square it, it becomes positive. So this thing can never be negative. In fact, the smallest thing this can be is 0, isn't it? Because if x was 4, you'd get 4 minus 4, 0, square that, still get 0. So this thing here has to be greater than or equal to 0. So basically, I've got something that no matter what x is, it has to be greater than or equal to 0. Add something that's 1. This whole thing here has to be greater than or equal to 1. And then clearly 1 is greater than 0, so I've showed it. There is no real value of x that you can put in here that makes this thing less than 0. Sick. Part 2 says, if I add 3 to a number and square the sum, the result is greater than the square of the original number. Woo! Statement of reason if the above statement is true, sometimes true or never true. Okay, so if you want to prove something, like if you think this thing's true, you're going to have to do it algebraically, because you're going to have to show that it is always true for every single value of x or whatever. If you think it's not true, so if you think there's like a, there's an example where it's not true, you can just find an example, like put in one number and it'll work. So for example, I think that there's probably numbers that this is true for, but there might be some that it isn't true for. So what's this saying? It's saying, right, if I take a number, as an example, 2. Take a number 2 and I square it. We know that's 4, right? And then it's also saying, right, well, if I then take this number, add 3 to it, then square it, that thing's always going to be bigger. And at first glance, this might seem true, right? Because look, 2 squared is 4. If I add 3 to 2, I'd get 5. Square that, I get 25. So then you're like, well, yeah, obviously, right? Like, if I have a bigger number, when I square it, it's going to be a bigger number. Like, 25 is greater than 4. And this generally works, right? Because, whatever, take 5 squared, and now add 3 to it, take 8 squared. 64, yeah, sweet. Generally makes sense. But what happens with negative numbers? Have a think about this. Imagine I had minus 10, okay? What is minus 10 squared? So here's the thing with negative numbers, right? The squares of them are still positive, because this is minus 10 times minus 10, it's 100. If I then add 3 to minus 10, I'm going to get minus 7. Square that and I get 49. So that one doesn't work, does it? So our statement is true here, but it's not true here. If I have these negative numbers, the actual if I add 3 to this, the magnitude or the size of this number is actually smaller. So when I square it, it's a smaller number. So it's not true here, is it? So if there are times when it's true and times when it's not true, then my final answer is just going to be it's sometimes true, isn't it? And that should do it for question 2. Question 3. Given that A as position vector 4i minus 5j, B as position vector minus 5i minus 2j, find the vector AB. Pretty basic vectors, this. So you can think of the i's and j's as like x and y coordinates, right? Like if I had this, if I had a little kind of 2D plane, 4i minus 5j would be 4 along here, and then minus 5 along here. So maybe like here. And that would be A, right? And then B would be minus 5i minus 2j, so it would be like minus 5i and then minus 2j maybe here. Then the question is like, how do I get from one to the other? And it's just going to be this line here. It's going to represent that line. But you're basically just going to do one take away the other. It's going to get you the differences between the x coordinates and the differences between the y coordinates. Essentially, so AB is just always going to be B minus A. Pretty simple. So in this case, it's just going to be minus 5i minus 2j, and then minus brackets 4i minus 5j. And that's going to get me that line, basically. So what i's am I going to get? Minus 5 minus 4 is going to be minus 9. Minus 2 minus minus 5 is going to be minus 2 plus 5, which is plus 3. Not too crazy. And then these lines basically mean the magnitude or the size of this vector. So if you were to think of this here, what this represents is that's basically saying now that I've got like minus 9 in this direction, So minus 9i, and then plus 3j. Which kind of makes sense, doesn't it, with this graph? So we get this nice kind of right angle triangle, and then this magnitude of AB will be represented by the length of this line, right? But we can use Pythagoras for this, can't we? Because we now know the length of this, which is 9. It's minus 9, but in terms of its size, it's just 9, right? And then this is 3. So if I just want this line, I'm just going to do the square root of 9 squared plus 3 squared. Simple as that, right? Now, it would not be difficult for me to do this in my head, but I've got a calculator. Why suffer, right? So if I just did 9 squared plus 3 squared and just square rooted all of that, it's going to be 3 root 10. So here's the thing, like, yes, I could work out that that's 81, that's 9, I get the square root of 90, and then I have to work out, put it in calculator, you know what I mean? And that's question 3 done. Question 4. L1 has equation this, so we're in straight lines, aren't we? And L2 passes through the points these two. Determine, giving full reasons for your answer, whether L1 and L2 are parallel, perpendicular, or neither. It's all in the gradient. It is all in the gradient. That is the only thing that determines if a line is parallel or perpendicular to another. So you might be fooled into thinking that you need to get the equation of L2. You don't. All you need is its gradient. So if I just get the gradient of L1, gradient of L2, it's going to be quite easy for me to compare the two things. So the gradient of L1, let's start off with that. Essentially, it would be nice if I could express this in the form y equals mx plus c. So let's do that now and see what we get. So let's add 3x to both sides. I'm going to get 4y equals 3x plus 10. I'm going to divide by the 4 to get y equals 3 over 4x plus 10 over 4. Yes, I can simplify this, but I do not need to because the only thing I care about is u over here, the gradient, which is 3 over 4. Now I'm going to do the same thing for L2, and I'm just going to compare the two. So how do I get the gradient of a line given 2 points? It's change in y over change in x, isn't it? So the gradient is going to equal, so it's basically y2 minus y1 over x2 minus x1. Difference in the y coordinates divided by the difference in the x coordinates. So it doesn't matter which one you take as like your first point and second point as long as you're consistent. So here I'm going to do 8. So taking that second set of coordinates as like my y2 and stuff. So I'm going to do 8 and then minus 1 because minus 1 is the y coordinate of the first. And then x coordinate, so it's going to be minus 1 minus 5. Simplify. What is 8 minus minus 1? It's going to be 9, isn't it? What is minus 1 minus 5? It's going to be minus 6. Can I simplify this at all? Well, I can divide through by 3, can I not? So this is going to be what? 3 over 2, and I've still got a minus sign there. Cool. So the two things we need to check are the following. Are the gradients the same? If they're the same, they're parallel, okay? They're definitely not the same, are they? This one is 3 over 4, and this one is minus 3 over 2. So let's call this M1, and let's call this M2. So M1 is definitely not equal to M2, so they're not parallel. And then the perpendicularity criterion is basically just saying if they multiply together to make minus 1, then they're perpendicular. Essentially, let's work out M1, M2. M1 is 3 over 4. M2 is minus 3 over 2. Do they multiply together to make minus 1? Well, I get a minus here. 3 times 3 is 9. 4 times 2 is 8. It's not minus 1, is it? So, they're not perpendicular either. Perpendicular, so they are neither. And I think that's it for 4, to be honest. Alright, what we got here? Another student that clearly doesn't use AI Tutor. So it says a student's attempt to solve the equation 2 log x minus log root x equals 3 shown below. Cool. So they start off writing down the equation. Sick. They then say 2 logs... mate. Here we go. So, okay. You might think that this first step makes sense. You say, okay, I know that if I have a log of something minus a log of something else, then I can basically say that that is log of a over b, assuming that the base of the log is the same. That works. At first glance, it looks like they've done that here, but the thing that they've like missed out is the fact that the first log has a 2 in front of it, and then the second one doesn't. So if you think about it, if I had a 2 here, I couldn't do that, because I've got log a minus log b, but then I've got another log a. Like, if I had a 2 in front of both of them, then I could factorize the 2 out and then use that. But the fact that there's a 2 in front of one of them, I can't do that. So here's what I would say. Generally say, like, use the power law first, because what we can do with the power law is we can bring coefficients up to the powers. Before using these laws, you want it so it's just like 1 log minus 1 log, or add 1 log. You don't want numbers in front of them, essentially. So that's the first mistake. So let's write that down, actually. So I would basically say, use the subtraction law, but, they didn't kind of account for the fact, or didn't, I don't know, take notice of the fact that there's no 2 in front of the that second term, basically. If there was a 2 in front of that second term, then that line would have been okay, because it's almost like factorizing the 2 out the front and then using the subtraction law. So that would be the first problem here, I think. But let's carry on. So what do they then do? They then say that x divided by the square root of x is the square root of x. That makes sense. They then say the following. Log 2... Okay, so I think that makes sense as well. They then use the power law. So they've brought this 2 up into the power. So you would get root x squared, which is x. Fair enough. They then undo the logs. So they go from log 2 of x equals 3. Now, their mistake is that if I was to undo this log, I actually write this. You can think of, the way I think of it is like the base going to the bottom. Base goes to the bottom, right? Because that's what a log is. This log, in words, is the following. What power do I need to raise 2 to get x? That's what the word definition of it is. So if we're told that the power you need to raise 2 to get x is 3, then 2 to the 3 equals x. But what they've done is they've said that it's 3 to the 2. So they've got those numbers mixed up, essentially. So I would basically just say for the second point, I would say, I don't know, just like mix the numbers and mix the base and the power up when they undid the logs, essentially. I assume that we're now just going to have to do it correctly. Write out the correct solution. Sick. Okay, so let's do this properly, right? So we start out, their first line is cool, they just copy the equation out. The next thing that I would do is, before using this subtraction, or let's get the 2 as a power of x, because then I'm just going to have like no numbers in front of the logs. So what I'm going to do is I'm going to say log 2x squared, that's the power law, and then minus log 2 root x equals 3. Now I can use the subtraction law, porque, because there's no numbers in front of these. So this is going to be log 2 and then x squared over root x equals 3. Let's simplify. So root x is the same as x to the half. And with x squared divided by x to the half, which would be x, let's write it out for you here. So I'd have x squared over x to the half, which would equal x to the 2 minus a half, which would equal x to the 3 over 2, right? So this is going to be log base 2, x to the 3 over 2 equals 3. Now I do this undoing of the log, but correctly this time. So the base goes to the bottom. So I'm going to get x to the 3 over 2 equals 2 to the 3. 2 to the 3 is 8, right? Cool. So I get x to the 3 over 2 equals 8. So how do I undo powers like this? I can kind of do it in steps, okay? So what I could do, for example, is I could cube root both sides, which is almost the same as doing like both sides to the power of a third, right? So if you were to think of it like this, you know, doing the same thing to both sides of the equation, right? Just doing left-hand side to the third, right-hand side to the third. The reason I've done this here is because that's going to cancel with that. So this is going to be x to the half. 8 to the third is the cube root of 8, which is 2. X to the half is the square root of x. So I can just square both sides now. So I'm going to get x equals 4, and that should do the job. Question 6. Company makes a particular type of children's toy. The annual profit made by the company is modelled by the equation this. So this is like a quadratic and complete in the squared form. P is the profit measured in thousands of pounds, and X is the selling price of the toy in pounds. Okay, so let's get this sketch up so we can actually have a bit of a talk about it. Obviously, it's quite simple in real life. There's a lot more going on. But basically, they're saying, look, imagine the company only sells this toy, right? So the toy is X. So the price of it. So the more expensive the toy is, the further to the right on the X-axis. And then they're saying, okay, well, like at a certain price, this is the profit that we make. So imagine if it's just super cheap and like down here, you might even be making a loss. This is like negative profit. Because if the toy is just so... You're selling your toy for 20p, you ain't making a profit, right? And then the price is going up, and then you start making a bit more money, right? And it's like, oh yeah, say maybe a tenner, whatever. We're making some money now. But then you keep putting the price up, and the price is just too high. People stop buying it. You know, they're just like, mate, I ain't paying 100 quid for this dead toy. You know what I mean? So your profit's going down at that point. And then maybe, you know, you're trying to charge 200 quid for it. Not a single person is buying it. So you're just running massive losses, aren't you? That's kind of what's going on here. It's saying price goes up. Yeah, sweet, we're making some profit. Goes up too much. You start losing profit. There's going to be some happy medium. I wish that in real life business was as easy as plotting a quadratic and getting the perfect pricing, but unfortunately it isn't. But, you know, we like these simplified situations in maths, right? So, basically, I assume that, you know, part of this problem is going to be like, well, what is this optimum price, right? Because that would be kind of the real-world application to this. Let's have a read of what the question's saying anyway. It says, using the model, explain why 15 quid is not a sensible selling price for the toy. Well, it'd be quite easy for us to just sub 15 quid into this and just see what profit we'd make out of it, right? So P would just equal 100 minus 6.25, and then X would be 15, minus 9 all squared. Stick it in your calculator. 100 minus 6.25 times 15 minus 9 squared, minus 125, right? Negative profit is a loss. So that would be minus 125. So if you would be selling it for £15, you would be losing £125,000 each year. According to the model. Okay. So according to model, you know, selling the toy for 15 quid would basically, you know, render a loss of 125 grand per year. Probably not the best idea. Part B says, given the company made an annual profit of more than 80 grand, find, according to the model, the least possible selling price for the toy. So, okay. So, part A, right? Like, what would that correspond to on this diagram? It would be down here, wouldn't it? Because this is this negative profit. So maybe X is 15 is here. So then I put that into the equation, I get this negative profit. Here, we're now saying that we've got a positive profit of 80,000, right? So at some point here, on the 80 here, because remember, this is measured in thousands, I hit a profit of 80 grand. So basically, if I had a profit of exactly 80 grand, there'd be 2 points, 2 possible prices here. It could be that one or that one. And it says of more than 80 grand. So basically, we could be anywhere here, couldn't we? Because all of this is more than 80 grand. So what would be the smallest value of the price, which would give me a profit of at least 80 grand? Well, it would be this one here, wouldn't it? Because this is the, you know, the leftmost X value. So how am I going to work this out? Maths, right? Because this is like a Y value or a P value of 80. I can just set it equal to this and see what I get. So if I was to do 80 equals 100 minus 6.25 times X minus 9 squared, I can just solve this equation. So what I'm going to do is I'm going to bring this over to the left and I'm going to bring that to the right. So I'm going to be left with 6.25 times x minus 9 squared, and then 100 minus the 80, so 20. I'm going to divide by 6.25 to get x minus 9 squared equals 20 over 6.25. I'm going to square root both sides, and be careful here because I do need a plus minus. So this is going to be plus minus the square root of this. Not going to touch my calculator yet, I want to wait till the end. And I want to add 9 to both sides. So my two possible x values, which would give me exactly 80 grand profit, would be 9 plus minus square root of 20 over 6.25. So at this point I can work it out. Which one is going to be the one that we care about? It's going to be the 9 minus it, because remember, we want the smallest possible value. So let's do 9 minus the square root of 20 over 6.25. It's going to get me some mad surd, but let's just put that into a decimal. And basically, I'm going to want 2 decimal places here, because that's money, isn't it? Right? You can have pounds, and then you can get like 100 pence in a pound. So you can't go any further than that. So basically, two decimal places in this case, I would basically get x as £7.21. Cool. The company wishes to maximize its annual profit. Makes sense. State according to the model the maximum possible annual profit. Okay, this isn't too difficult because we already have this completed the square format, right? So it's basically going to be this maximum point. We can get that from completing the square. It's basically going to be the negative of whatever this value is. Because essentially, this is going to get maximized when this thing is 0, isn't it? Because if I have 100 minus something, I don't want to minus anything from that profit. So because this is a square number, the smallest value this can be is 0. So that's going to be the value which maximizes profit. So this point, when is this 0? It's when x equals 9. And then what would the p-value be? Well, it would be 100 minus 0, which is 100. In other words, the maximum possible annual profit is going to be 100 grand. Make sure you remember the thousands here. And the selling price for the toy that maximizes this annual profit is going to be £9. Completing the square, mate. What a thing. In a triangle ABC, side AB has length 10, AC has length 5, angle back equals theta, where theta is measured in degrees. Area of the triangle is 15. Find the two possible values of cos theta. So this is interesting, right? Because I suppose we're going to make some equation and we're going to get, from the information we have, we're going to get theta. Why would there be two possible values? So let's have a bit of a think about this. If AB is 10, so I've got A, B is 10. Are there different possible ways of getting this? So the first kind of thing worth thinking about is AB has length 10, AC has length 5, right? But then we're not told what theta is. So AC could look like that, because that's, got a length of 5. But it could also look like that, right? They both satisfy this AC being of length 5. So this would give two possible configurations of this triangle, wouldn't it? It would give this. That's completely legal, given all of the information that we've just been given. But we could also have this, could we not? Right? Like, in both cases, this length is 5, and this length is 10. So this is a legal triangle, right? So this is why I think there are two separate values of cos theta here. So theta is angle what? BAC. So it's going to be this. So it could be that, or it could be that. Right. Area of the triangle ABC is 15. So I think we can use that equation to work out these possible values here. Okay, so how do we get the area of the triangle, right? Well, area tends to equal a half AB sine C. Now, I need to be careful about the arrangement of these letters. So the A, B, and C might not correspond to the A, B, and C in your triangle. It just means, in general, C is going to be the angle in between these two lengths A and B. So in this case, does this work out? This kind of does, doesn't it? So let's think of it like kind of in the black triangle sense. This is going to be my value of theta, right? So my area is going to be 1/2 times 5 times 10 times sine theta. And then in the red sense, it's going to be all of this. So it's going to be, 1/2 times 5 times 10 times this sine of theta. So let's work this out quickly. So this is going to be 1/2 5 10 sine theta, and we're told that this is equal to 50. Sick. Let's work this out quickly. So 5 times 10 is going to be 50. Half that, I get 25. So I'm going to get 25 sine theta equals 15. Divide by 25, I'm going to get sine theta equals 15 over 25. Let's cancel a 5 here, so this is going to be 3 over 5. Okay, we can see here that in this configuration, this theta is acute, it's less than 90. And then in this one, it's obtuse, isn't it? It's more than 90, kind of all of that there. It's a big old angle. So let's think about sine theta here. I'm going to quickly draw the sine graph here. We like drawing the trig graphs. So does this kind of make sense? Well, sine looks like this. So do I have an acute and an obtuse possibility for sine theta equaling 3 over 5? I do, because if 3 over 5 is here, we can see here that it could be this angle, which is acute, because this peak is at 90 here. So it could be that, or it could be this thing here, which is obtuse, because it's after 90. So to get the first one, what I need... okay, so this is interesting, actually. We want the two possible values of cos theta. So, yes, I could undo this. I could get the inverse sine and then put it into cos, but I could probably be a bit more clever. So, if I was to, for example, use the identity, cos squared plus sine squared equals 1, I can get the value of cos theta from the value of sine theta without actually getting the value of theta. So essentially, if sine squared theta is 3 over 5, I can get what? I'm going to get cos squared theta plus 3 over 5 squared equals 1. So this is going to be cos squared theta plus 9 over 25 equals 1. Take the 1 over to the other side. So I'm going to get cos squared theta equals 1 minus 9 over 25. You can put this in your calculator if you want. Essentially, 1 is 25 over 25. So I'll take 9 over 25 away from that. I get 16 over 25. So what I can now do is I can square root, can't I? So I can say that cos theta equals, remember I need to plus minus square root of 16 over 25. And this is quite nice, isn't it? Because they're both square numbers. So this is going to be plus minus 4 over 5. Now, you might think, wait, can I have a negative value of cos? You definitely can. Because if you think about the cos graph, it goes like this. So if theta is obtuse, so this is 90 degrees. So if I have a cos value where the theta is more than 90, it's going to give me a negative cos value. So this is completely fine here. So this kind of makes sense, doesn't it? Because I might have positive 4 over 5 here, which would give me this acute angle. And then negative 4 over 5 here, which would give me an obtuse angle. Completely allowed. Sick. So yeah, two possible values of cos theta are going to be plus minus 4 over 5. That's actually quite tough. I'll give you that. That's not too easy. There's a bit going on there, a bit of understanding. Given that BC is the longest side of the triangle, find the exact length of BC. Okay, let's go up to our diagram quickly. If BC is the longest side of the triangle, which configuration do we have? In the black one, BC is not the longest side, is it? 10 is the longest side. In the red one, BC is definitely the longest side here. So which value of theta does that correspond to? It's going to be the obtuse one, isn't it? The one bigger than 90. And which value of cos does that correspond to? The minus 4 over 5. So we now know that theta is bigger than 90 and that cos theta is equal to minus 4 over 5. Okay, so how do we get the length of BC? Let's look at this triangle again. And let's actually be clever here and copy and paste, because it would be nice to have all of this down here. So, what are we doing now? We essentially have the red one, don't we? So if we get rid of this, here we are. Okay, so we want the length BC. We actually have quite a lot of information here. We don't have theta, but we have the value of cos theta. So if I was to do the cosine rule, what am I going to get? Well, this is A. So I'm going to get A squared equals B squared plus C squared minus 2BC cos A. This A is theta in this case, shove it all in. So A squared is going to be 5 squared plus 10 squared minus 2 times 5 times 10 and then times minus 4 over 5. Negative cos values are completely okay in this context, so do not worry. So I'm going to get 5 squared plus 10 squared minus 2 times 5 times 10 and then times minus 4 over 5. And I get A squared is 205. All I need to do is square root now. And I want the exact length, so I'm definitely going to want to keep my answer in surd form. You know what, my calculator isn't even simplifying it at all. So this is going to be my final answer for the length of BC. A lorry is driven between London and Newcastle. In a simple model, the cost of the journey C, when the lorry is driven at a steady speed of v kilometers per hour, is all of that stuff. Find, according to the model, the value of v that minimizes the cost of the journey. Okay, so minimum, okay, part B says prove, sweet. Minimum and maximum values you get using differentiation, okay, and you get them by setting the derivative equal to 0. Why is that? Because if I have some function that I can plot, the minimum and maximum values are going to be when the gradient of this tangent here is equal to 0, right? When the tangent is flat. So basically, all we do to find these points is set the derivative equal to 0. So if I was to work out dc by dv here, you know what, let's rewrite c first. Just like the integration question, the first question in this paper actually, it's useful to write everything in terms of just their powers. So this first term I'm instead going to write as 1500 v to the minus 1. And then, you know, plus 2 over 11 lots of v plus 60. Now I can differentiate relatively easily. So this is going to be dc by dv in this case, right? So bring the power to the front, so minus 1500. And then take 1 from the power. And then this thing here, 2 over 11v, is basically just going to go to 2 over 11. And then the 60 does not differentiate to anything because its power of x is 0. So that is going to be dc by dv. To get the stationary point, I am going to want to set this thing equal to 0. So I am going to basically say minus 1500. Now, v to the minus 2 is basically the same as divided by v squared. Plus 2 over 11 equals 0. Let's take this over to the other side. So I'm going to get 1500 over v squared equals 2 over 11, and I got myself an equation, haven't I? So let's multiply it by v squared. And then I'm going to want to get the 2 over 11 over to the other side. So times by 11 divided by 2. So I'll get 11 times 1500 over 2 equals v squared. And then just square root it, right? So we know that v, you know, is just the speed, right? So it's going to have to be positive. So all I need to do is take the positive square root of this. And that should tell me the value of v. So it's interesting here, actually. And the reason I paused at the start of this was because this technically, I don't know that this is kind of the value that minimizes the cost. I just know that it's a stationary point. So it could be a min or a max. But then I looked at part B, and it said, okay, we'll prove by using that the cost is minimized at that. So that's when we actually have to show that this stationary point is a minimum, basically. So essentially, let's get the value of v here. So I'm going to do the square root of 11 times 1500 over 2. And I get 5 root 330, but that's not very useful. So let's get that into a decimal. So it's going to be 90.8295 dot dot dot. Let's go 3 sig fig. So I'm going to say 90.1, and this is what? Kilometers per hour. Nice. The minimum cost of the journey. So this is now going to be, I just need to sub in this value of v to c, right? So c is just going to equal 1500 over this value of v now, so this 90.1. Now I'm going to write 90.1 dot dot dot. The reason is, when I put this into my calculator, and I know I say this in every video, I'm not going to use 90.1, I'm going to use the answer in here because that's got all of the accuracy. If you're using numbers in future calculations, try to use the unrounded version because we don't want rounding errors here. That's why I'm putting the dot dot dot, to show that what I'm going to be putting into my calculator is actually the whole thing. So plus 2v, so the 90.1 bar 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 over 11 plus 60. And the good thing is here, because I've got it stored as ants in my calculator, I just use that. So I'm going to do 1500 over ants plus 2 times ants over 11 plus 60, which gives me, again, equation said, get it into a decimal. Looks like this is going to get me 93.0289 blah de blah de blah. Now this is in pounds, isn't it? So it would be useful again to round this to 2 decimal places because that's pence, right? So rounded to 2 decimal places is going to be 93 point and then what? 03 pence. Fantastic. So as I was saying before, we've actually only shown that this is a stationary point. We've not shown that it's a minimum. But now it says prove using the second derivative that this cost is minimized. So this is now where we go, okay, work out the second derivative. So d2c by dv squared. We just need to differentiate the first derivative. So the first derivative was this stuff. So minus 1500 v to the minus 2 plus 2 over 11. Stick this here. Okay, so I want to differentiate this thing here. So bring the power to the front. So it's going to be minus 2, so plus 2 times 1500. Take 1 away from the power, and then the number goes away, doesn't it? So that's my second derivative here. Cool. So this is what? This is 3000 over v cubed. So it doesn't actually matter what v is in this case. This thing is always going to be positive, right? Because, you know, v is positive, so v cubed is positive. This is positive. So I don't even care what v is. This is going to be positive. So my stationary point, basically, if d2c by dv squared is greater than 0, it's a minimum. Semi-counterintuitive, but you need to remember that. If it's less than 0, it's a maximum. State 1 limitation of the model. I mean, we've just basically proven that if this lorry driver bombs it at what, 91 kilometers an hour? Consistently, like perfectly, all the way from London to Newcastle, crossing the country at 91 kilometers an hour. It's just not realistic, is it? You know, how is he going to stay, you know, no traffic lights, no traffic, no stopping, absolutely nothing, just straight. It's just not going to happen. It's never going to happen, is it? So it's just unrealistic, basically, to maintain that speed, you know, from London to Newcastle, like, absolutely no chance, mate. And I believe that'd actually do the job for question 8, burning through it. Question 9, g of x is some cubic. Use the factor theorem to show that x plus 2 is a factor of g of x. Super simple. All you need to do is sub the number that would make this bracket 0 in. So this would be minus 2, right? If x was minus 2, x plus 2 would be 0. This thing should equal 0 when I stick it into the function. So all I need to do is work out 4 times minus 2 cubed minus 12 times minus 2 squared minus 15 times minus 2 plus 50, and I will put money on this thing being equal to 0. 4 times minus 2 cubed minus 12 times minus 2 squared minus 15 times minus 2 plus 50. Boom, 0. Who would have thought? Therefore, x plus 2 is a factor. Nothing too crazy. Looks like I am shouting it. Sick. Part B. Hence show that g of x can be written in the form g of x is x plus 2 multiplied by ax plus b squared. A and b are integers to be found. So I want to fully factorize this, right? I know that this is a factor, so what I can do is do long division to work out what the other bit should be. So, lo que tengo que hacer es do x plus 2 and divide that into the g of x. So this is going to be what? 4x cubed minus 12x squared minus 15x plus 50. Okay, how many times does x go into 4x cubed? It goes 4x squared. Multiply it through. 4x squared times x is 4x cubed, which it should be by design. These should always match up. Plus 8x squared. Take them away. This goes minus 12x squared minus 8x squared is minus 20x squared. And then if you want, you know, you've essentially got what? Minus 15x minus 0 plus 50 minus 0. Repeat. How many times does x go into minus 20x squared? It goes minus 20x. Multiply it through. So I get minus 20x squared minus 40x. I know I'm going through this quickly. You know, I don't want to spend ages on this technique because I'm just doing an exam video. Take these away. Cancels out. Minus 15x minus 40x is going to be positive 25x. And I've still got the 50. How many times does x go into 25x? 25 times. Multiply it through. 25 times x is 25x. 25 times 2 is 50, and this should get a remainder of 0. We knew that it should get a remainder of 0 because we were told and we proved that x plus 2 is a factor of this. Therefore, g of x can be written as x plus 2 multiplied by this. So 4x squared minus 20x plus 25. Can I factorize this any further? I think I can. The first thing is I know that I'm going to be looking for some squared bracket. So I know that whatever these things are, they have to be the same, okay? So what's the only way I can get 4x squared using two of the same numbers? It's going to be 2x, right? Why is that going mad? So I'm going to have 2x. What's the only way I can get 25 using two of the same numbers? Well, it's going to be 5 or minus 5. It's going to have to be minus 5 here because this is minus. So if you were to multiply this out, you'd get 2x times 2x, 4x squared. Minus 10x minus another 10x, so minus 20x. Minus 5 times minus 5 is plus 25. So that works out. Meaning that g of x is x plus 2 times 2x minus 5 all squared. Sick. Part C says figure 2 shows a sketch of the curve with the equation y equals g of x. So we've got it here. Use your answer to part B and the sketch to deduce the values of x for which g of x is less than or equal to 0. Okay. Well, g of x being less, the y coordinate is g of x here. So it is less than or equal to 0, kind of here, but also it's equal to 0 here. It just touches it, doesn't it? So this, it's going to be less than or equal to 0 because it's going to be equal to 0. And then here it's going to be less than and equal to 0. So we essentially kind of need like this and then kind of all of this stuff down here. Okay, well, obviously the answer to part B is going to help here. Because if we had g of x in this form and we said, when is this thing equal to 0? We can get our values of x relatively easily, right? Because this equals 0 when either x equals minus 2, which is clearly going to be that, or x equals 5 over 2. And because this is squared, this means we have this repeated root and we get this thing happening. So we know that this bit's 5 over 2 and this bit's minus 2. Therefore, g of x is less than or equal to 0 when x is less than or equal to minus 2, because it's all of that stuff over there on the left, or when x is just equal to 5 over 2, g of x is going to be equal to 0. And they're the only two parts, aren't they? Sick. G of 2x is equal to 0. Okay. Well, let's look at this graph here. What would happen if I was to sketch g of 2 of x? Like, what transformation does that correspond to? It's going to correspond to a stretch in the x-axis of scale factor a half. In other words, it's actually going to squish this thing in horizontally. So it's kind of going to look like, I'm not even going to try it, but it's like all of the x values essentially get halved. So like this -2 would turn into a -1. You know, it kind of like just proper, everything would go in. You know what I mean? That 5 over 2 would kind of shoot over there. That -2 would shoot over here. Everything just halves in size on the horizontal axis. So when is it equal to 0 now? Well, this term corresponded to the -2, so that's going to be half of it. So it's going to be -1. And then this, which corresponded to the 5 over 2. This is an awful sketch, by the way, because this actually should have gone like that. That was just not good at all. Essentially, that should have bounced up here. That was completely my bad. So that should have gone like that, essentially. So the 5 over 2 actually gets transported over here. So what is half of 5 over 2? It's just going to be 5 over 4. And that, basically, is going to be the answer to question 9. First principles, I'm going orange. So you do get this in your formula booklet, so don't worry too much, as long as you know where it is in the formula booklet, right? Basically just tells you that, look, f of x, f prime of x, so the derivative of f of x is the limit as h tends to 0 of f of x plus h minus f of x over h. Simple as that. So in this case, what is f of x? It's going to be x cubed. So all I need to do is let's work out f of x plus h before I stick it in here. So basically, I'm going to do a bit of the old binomial expansion here. Essentially, if you think of Pascal's triangle, the coefficients of this expansion are going to be 1, 3, 3, 1. So I'm going to have like a 1, 3, 3, and a 1. And then the powers are kind of going to go like this. So x cubed is going to start, well, at cubed, h to the power of 0. And then it's going to be like x squared, h to the power of 1, xh squared, x to the naught, h to the power of 3 kind of thing. So this is going to be an x cubed. Let's write it all out, h to the naught. This is going to be an x squared h. This is going to be an xh squared. And this is going to be an x to the naught h cubed. In other words, it's going to be x cubed, that's 1, plus 3x squared h plus 3xh squared, that's 1, so plus h cubed. Stick it into the fraction and you should be laughing. So, I am going to get all of this. Because I'm lazy, I'm going to copy and paste it. Right, what else? I'm going to have minus f of x, so that's going to be minus x cubed. All over h. Cool, okay. So the whole point of this is that right at the start, I can't sub h equals 0 in, because I get 0 over 0. But then I can do some algebra that kind of cancels this 0 over 0 and it works out. So look at this. I've got an x cubed here and an x cubed there, so I can cancel those out, right? So I'm basically just going to be left with everything in the middle. So I'm going to have 3x squared h plus 3xh squared plus h cubed over h. This is now useful because I can actually cancel an h, can't I? So this is going to be the limit, as h tends to 0, of 3x squared plus 3xh plus h squared, and then there's actually no over h anymore because I've cancelled it. So here's the thing, at this point, putting in an h equals 0 and get 0 over 0 wouldn't make any sense. But I've done the little algebra, and look what I can do now. It's completely viable for me to sub h equals 0 in, because this term goes, and I get 3x squared. And there's no mad math errors floating about. So that is literally it. Oh, look at this. A bit more binomial for the next question as well. So we want the first 3 terms of this thing. Okay, so it's not going to be much kicking off. Essentially, as I said before, right, like First term starts at the highest power and the second at the bottom, and they kind of just go like this. So the first term, right, is going to be, it's going to correspond to 2 to the power of 9 and then minus x over 16 to the power of 0, right? The next term is going to be 2 to the power of 8 and then minus x over 16 to the 1. So these powers are always adding up to 9. The next term would be 2 to the power of 7 minus x over 16 squared. And then there'd be a load of others, but luckily we only need the first 3. So this isn't the whole story because we also have these coefficients. So the coefficient is going to be the kind of NCRs. So it's going to be 9C0, and then it's going to be a 9C1, and then it's going to be a 9C2. And then I get a plus dot 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 because there's actually more terms going on here. Okay, so 9C0 is actually, anything C0 is always 1. 2 to the 9 is a big old number. It's 512. And then this is a power of 0, so nothing actually happens there. So that'll be 512. 9C1 times 2 to the 8. Okay, let's work that out. So 9C1 is going to be 9. Times that by 2 to the 8. And I get 2,304. And then that's going to be times by minus x over 16. And then this term here, let's do this number, then think about that later. So 9C2 times 2 to the 7. So I'm going to do 9 and then shift divide to get me that C, stick a 2 there. And then I'm going to multiply that by 2 to the power of 7 to get me 4,608. It's going to be times minus x over 16 squared. Okay, first term 512, cool. Second term, I'm going to get a minus from here, and then it's going to be 2304 over 16. So 2304 divided by 16 gets me 144 lots of x. And then this, the minus squares out, so it's going to be positive. And then the 16 is going to square out as well on the bottom. So if I do 4608 divided by 16 squared, that will get me 18. So it's going to be 18, and then this is going to be an x squared. So not too shabby in the end. Cool. Given that the first two terms in ascending powers of x in the series expansion of that disgusting thing there are 128 and 36x, find the value of a. Right. Oh, okay. So here we've now got a function that is a plus bx multiplied by that thing that we've just done. So instead of writing 2 minus x over 16 to the 9, what I'm going to do is I'm going to write the expansion that we just worked out. So I essentially have a plus bx multiplied by this, don't I? By 512 minus 144x plus 18x squared. And then there are more terms in here. So we're told about the first two terms in ascending powers of x in the series expansion of this thing here. Okay, so the first two terms are going to be the number term and the x term, right? So how am I going to get, from multiplying out these brackets, how am I going to get the number term? What is the only combination of things here that I multiply from both of the brackets to get a number? Well, the only way I can do this is a times 512, because everything else has an x in it, doesn't it? So I know that 512a is going to be my first term, my number term here. And then it's just a case of getting the x terms. So what are the different ways I can get x terms? Well, I could do a times minus 144x. So let's work that out. That's going to be minus 144ax. But that's not it, is it? Because I could also do bx times 512. So it's going to be plus 512bx. Now, a quick check over. Are there any other ways I could get an x term? I don't think there are. Because now I could do x times x, but that gets x squared. X squared here times anything is going to be x squared or above. So I think that's it. So here's the thing. When we have these binomials multiplied together, you might think, oh, mate, it's going to be grim. But then once you actually write it out and you say, you know what? I don't have to do this whole expansion. I just pick and choose the terms I want. Like, if you were to have done all of this and then all of this, you just don't need to do that because you would have only picked 3 terms of that anyway. So it's not too bad. So grouping these terms, I get 512a is my number term. And then my x term is going to be 512b minus 144a. Sick. Okay, and now we are told that the first term is 128. In other words, this must equal 128. And then the second term is 36x. In other words, this thing here must be 36. Not too bad, is it? Because all we do now is we say 512a is 128, which tells me that a is 1 to 8 over 512. Believe this is going to be a quarter, but let's just check. 1/4. And then let's sub this into the second equation here. So we know that 512b minus 144a, which we now know to be a quarter, is equal to 36. Okay, 144 times a quarter is 36. So I get 512b minus 36 equals 36. Add the 36 onto both sides. I'm going to get 512b is 72. So b is going to be 72 over 512, which is going to equal 9 over 64. That is going to be A and B, and that is going to be question 11 done. Question 12, I think we're getting there already. So it says, show that the equation 4 cos theta minus 1 equals 2 sin theta tan theta can be written in the form 6 cos squared theta minus cos theta minus 2 equals 0. So we definitely want to be using identities here. Essentially, in year 12, there are basically just two identities that you need to know. And that is that tan is sine over cos, and then cos squared plus sine squared equals 1. So when I just have coses and sines, I'm basically in the realm of cos squared plus sine squared equals 1, right? So the tan's a bit weird. What I could potentially do is swap the tan out for sine over cos, and then I've just got coses and sines, and then I think I'm going to be able to use the cos squared plus sine squared equals 1 in some way. So what I'm going to do is I'm going to rewrite this tan here. Sine over cos. Let's see if we can simplify this at all. So the first thing is I can just multiply this sine on the top. So I almost get 2 sine squared over cos theta. What I can now do is multiply both left and right by cos theta. So I'm going to get 4 cos squared theta, right? Minus cos theta equals 2 sine squared theta. And this is what I mean. I'm now in the realm of coses and sines. I can swap out a sine squared for 1 minus cos squared, can't I? So this here is going to be 2 times 1 minus cos squared theta. And I think I'm almost there, to be honest, because this 2 minus 2 cos squared theta. Add it all to the other side. So add 2 cos squared theta. I'm going to get 4 cos squared theta plus 2 cos squared theta, which is 6 cos squared theta. And I think I'm going to be sorted. Because I'm going to... Well, that's just the cos theta, so let's leave that there. Minus the 2. And that should be my answer. Cool. Part B, I think, is going to be quite instructive. So it says, solve for x between 0 and 90. Okay. Look at this equation. 4 cos of 3x minus 1 equals 2 sine 3x tan 3x. It's clearly the equation from above, right? Says hence, so you know that you're going to be using what you just did. But instead of theta, we have 3x. So I really want you to be careful about this. The first thing we know, by the way, is that for part A, this applied to any theta, okay? So we can basically say for part B that this equation that we have in part B, 4 cos of 3x minus 1, all of that stuff, can be written in the form 6 cos squared 3x minus cos 3x minus 2 equals 0, can't we? Because, again, we've showed that, that applies to theta, it therefore applies to x or 3x or whatever. Sick. Okay, so we can kind of solve this, but I want to be careful here. X is between 0 and 90, but the variable I'm actually caring about here is like 3x, right? So always do this. Change your range before you get stuck in, okay? So if x is between 0 and 90, then what is 3x between? Well, I need to triple my range, do I not? So 3 lots of 0 is 0, 3 lots of 90 is 270. You need to do this, because if you don't, you will lose solutions. So what I'm going to do is I'm going to solve this thing as if I was solving it for 3x, and then only when I've got all of my solutions, do I then divide by the 3 to get the x values? Cool. So here's basically a quadratic. If you don't believe me, why don't we let y equals cos of 3x? If we were to do that, we would get 6y squared minus y minus 2 equals 0. Cool. So we can factorize this. I'm in the business of making my life easy. So if you can factorize it, good on you. I can't really be bothered, to be honest. So what I'm going to do is I'm going to click menu on my calculator. I'm going to go down to A, which is equation func. I'm then going to press polynomial, degree 2. A polynomial of degree 2 is a quadratic. And you can see here that I have this ax squared plus bx plus c. So I'm going to put my coefficients in here. So the x squared, or y squared in my case, coefficient is 6. The x is going to be minus 1 because I've got minus y. And then the term on the end, the number, the c, is going to be minus 2. If I press equals now, it tells me my solutions. So this tells me that y is going to equal 2 over 3, or y is going to equal minus a half. Easy as that, right? No factorizing, no worries. So what I'm going to do now is I'm going to say, well, these aren't actually y, these are cos of 3x. So I've essentially got two trigonometric equations I need to solve. Cos of 2x equals 2 over 3, sorry, of 3x, and cos of 3x equals minus a half. Now, we can just sketch the cos graph here. Because I've done that stuff with the range, we're almost imagining that 3x is just our variable. So let's sketch the cos graph out. It kind of goes down like this, and then up like this. Now, my range here is 0 to 270. This is 270. So what this tells me is I'm actually only looking for solutions between here and then here, basically. So I'm working within the red walls. So what I'm going to do is I'm going to draw horizontal lines corresponding to 2 over 3 and minus a half, and then we're going to see where these graphs intersect. So 2 over 3, positive number, could be around here. Minus a half, around here. Okay, so this tells me that I'm looking for one solution from the 2 over 3, but two solutions from the minus a half. So I'm going to need to use some symmetries there. Okay, so my first value for 3x is going to be, at this point I can just get my calculator out and do the inverse cos. Make sure you're in degrees and then do the inverse cos of 2 over 3. This is going to get me 48.189 ... That's cool. And then, how am I going to get it for this? Let's do inverse cos of minus a half, and let's see what I get. So I'm going to do inverse cos of 0.5. That gets me, not 0.5, minus 0.5, right? So this gets me 120 degrees. This makes sense, because this here is 90, so this 120 does make sense, it's after 90. So that's going to be one of them, 120. How am I going to use the symmetries of the cos graph to get this? This is 0 and this is 120. So this horizontal distance here is 120. Do I have a corresponding horizontal distance on the other side of the graph? I do. It's going to be the distance from 360 to my other solution down here. So that is also 120. In other words, to get my last solution, I need to do 360 minus 120 to get me 240. And they're my three solutions. So all I need to do now is divide through by the 3. Only do that once I've got all of the solutions. So my x values are going to be, let's write this thing out, so 48.189 over 3. And then to one decimal place, this is going to get me 16.1 degrees. 120 over 3 is going to be 40 degrees. 240 over 3 is going to be 80 degrees. And we can see here that all of these final x values lie within the initial range I was given. Question 13 is an absolute classic. It's this log modelling that they just love to go over. So it says the value of a rare painting, V, is modelled by the equation V equals PQ to the T. So it's exponential, isn't it? Where P and Q are constants and T is the number of years since the value of the painting was first recorded on the 1st of January 1980. The line L shown in figure 3 illustrates the linear relationship between t and log 10 of v since the 1st of January 1980. The equation of this line L, it's like a y equals mx plus c, isn't it? It's like a log 10v equals 0.05t plus 4.8. Find to 4 significant figures the value of p and the value of q. Okay, so the whole point here, right, is that we have an exponential relationship. PQ to the t. This is not a straight line, is it? It's exponential. It goes like that. It curves. It's blah, blah, blah. It's not nice. Not a nice straight line. If I take logs of this, it makes my life really easy. And if I, instead of plotting v against t, I plot log 10 of v against t, it's a straight line. Why? Let's take logs of both sides. Log 10 of v equals log 10 of p q to the t. I can use a log law to split these two things up. So I'm going to say that this is log 10 of p plus log 10 of q to the t. I can now use the power law here. So this is log 10 of p, unchanged. And then this is going to be t log 10 of q. Why is this useful? Look at what the equation of a straight line is. So the first thing I'm going to do, I'm going to rewrite this. I'm just going to write log 10 of v, and then I'm just going to swap these two terms, and I'm going to write this in front of the t. But that doesn't change anything, does it? So I've got log 10 of q times t plus log 10 of p. What's the equation of a straight line? Is it not y equals mx plus c, right? Log 10 of v, if you look at the graph, that's my y value. That's what I'm plotting on the y-axis. X, well, t, that's what I'm plotting on the x-axis, the horizontal one. Meaning that this is going to be a straight line. My value of m, my gradient, is just going to be log 10 of q. And my value of c, my y-intercept, is going to be log 10 of p. And we know this because, look, we're even told the equation of the line, aren't we? We're told that the equation of the line is log 10 of v equals 0.05t plus 4.8. So instantly I know that what? Log 10 of q must equal 0.05 and log 10 of p must equal 4.8. This is so classic. Like every single AS paper they ask you this. They absolutely love it. So this thing here is going to be 4.8. I can get p and q from this by just undoing the log. So q is going to equal 10 to the power 0.05. P is going to equal 10 to the power of 4.8. And I want these four significant figures. So q, stick it in the calculator, 10 to the power of 0.05. Let's write out loads of sig fig and then I'll round it after. So it's going to be 1.122018, that'll do. And then p is going to equal 10 to the power of 4.8, which is going to be 63095.73445. Madness. Okay, and then to 4 sig fig, obviously we're going to get what? So 1, 2, 3, 4 sig fig, so 1.122, yeah, that's 4 sig fig. And then p to 4 sig fig is going to 1, 2, 3, 4. So that's going to round up to a 10, which would then make that a 1. So it's going to be 63,100. With reference to the model, interpret the value of the constant p and the value of the constant q. Okay, let's have a look at the model again. The model is v equals p q to the t. So if you were to imagine the value for different years, right? So t is 0, t is 1, t is 2, the value of v. If t is 0, v is going to be p times q to the 0. Well, q to the 0 is 1, so it's just going to be p. So that instantly tells me something, doesn't it? That tells me that p is just the initial price of the painting, right? So p is going to be the initial price of the painting because time t equals 0. So initial price of painting, you know, when t equals 0, so it's going to be the price, you know, it was sold for on the 1st of January 1980. So what? It's going to be 63 grand, not bad for a bit of paint. Now, what happens as t goes up? So if t equals 1, so like 1 year later, what's going to happen? Well, I'm going to get P times Q to the 1. In other words, P times Q, right? T times 2, I'm going to get P times Q squared. So P times Q squared, what's happening to get from one year to the next? I just multiply by Q each year, don't I? So Q is almost telling me like my increase or my proportional increase in value of the painting. Another way to think about this, Q is 1.122, right? So imagine I take a number and I multiply it by 1.122. What does that do to the number? Maybe think of this in terms of a percentage. That basically corresponds to a 12.2% increase, doesn't it? So the fact that Q is 1.122 essentially corresponds to the fact that my percentage increase, so the percentage increase of the value of the painting each year is what? It's 12.2%. Because if I multiply a number by 1.122, that is essentially the same as adding 12.2% to its value. So Q is like this proportional increase and P is the initial price. Find the value of the painting as predicted by the model on the 1st of January 2010, giving your answer to the nearest £100,000. So this is going to go mad, I reckon, if it's going up by 12% each year. Okay, well, how many years later is 2010? It's 30 years later, isn't it? Same date each year, add 30 years, you're in 2010. So all I really need to do is I need to work out, so it's PQ to the T, isn't it? If T is 30, I'll just work that out, don't I? So it's going to be PQ to the 30. Okay, so I am inclined to use the unrounded values of P and Q here. I think that would be much better. So if I was to instead grab these values here, just to avoid any rounding errors, right? I don't like using rounded values. So what I'm going to do is I'm going to use these unrounded values in my calculator here. So what I'm going to do is use 1 point this for Q. So essentially I'm going to write 63095.73445, just so I get as much accuracy as possible. It's rare that it's really going to make much of a difference, but it's better to be safe than sorry. So times 1.122018 to the power of 30. Just stick that in your calculator. So 63095.73445 times 1.122018. I think this is going to be massive, by the way. 199,5238.079. So we're super, super close. How many numbers are this? Woo, is that 2 mil? That's 2 mil, isn't it? Paintings, man. Look at this. This is 2 because there's 6 zeros here. Okay, so it's the nearest 100,000. So this is £1,995,238. So super close to 2 mil. So the nearest 100,000, this is going to be 2 million quid, isn't it? 1, 2, 3. So not a bad little investment. Question 14. Nice and quick today. Okay, so it says the circle C has equation, all of that stuff. Find the coordinates of the center and the radius. Okay, absolute classic, right? So we know that if we have a circle of the form this, why have I just forgot how to write? There we go. That instantly tells us the center and the radius. So the center in this case would be AB and the radius would be R. So the problem is we've not got it in that form, have we? But if we were to complete the square, it will get it in that form. So we need to complete the square on the x terms and the y terms. So looking at the x terms, I've got an x squared minus 6x. So that would turn into an x minus 3 squared minus 9. The y terms are y squared plus 10y, so that would turn into a y plus 5 squared minus 25. And then I've got a plus 9 chilling on the end anyway, and that equals 0. Clean this up, and it's in the form, isn't it? So I'm going to have x minus 3 squared plus y plus 5 squared. Okay, I've got a minus 9 and a plus 9, so they're going to cancel. I've got a minus 25, so if I add the 25 to the other side, I get that. Which is sweet, because it's a square number, isn't it? So the center is going to be 3 minus 5. Essentially, it's the opposite of the sign that's in the bracket. And the radius is going to be the square root of 25, which is 5. Cool, that'll do the job for part A. So the line with equation y equals kx, where k is a constant, cuts C at 2 distinct points. Find the range of values for k. Okay, there's a bit going on here. Essentially, let's imagine that the question instead said, find where these two lines intersect. Or, well, the line and the circle intersect. What would you do? Well, you would solve these things simultaneously, wouldn't you? So you would essentially solve the simultaneous equations y equals kx and all of this stuff. Or we could go, let's use the top equation here, actually. Yeah, let's use the top equation. So the equation, x squared plus y squared, let's write it down. So I'd almost have an equation 1 here, and an equation 2, which would be x squared plus y squared minus 6x plus 10y plus 9 equals 0. Okay. So imagine it said that. Imagine it said, find where these two things intersect. What would you do? Well, you would solve them simultaneously. So in this case, I would probably sub this value of y into the second equation, because we already have it nicely rearranged. So I would say that x squared and then plus y is kx, so we would instead have kx squared minus 6x plus 10kx, because that's y, plus 9 equals 0. Let's clean this up. So let's think of my x squareds here. I'm going to have x squared and then plus k squared x squared minus 6x plus 10kx plus 9. What type of equation is this? It's quadratic. I've got x squared terms, x terms, and number terms. So let's group them. Here, I'm going to have 1 plus k squared lots of x squared. I'm going to have 10k minus 6 lots of x, and then I'm going to have a plus 9. So, let's imagine now. Obviously, as it stands, there's unknowns here. So I've not really got enough information to work things out. However, what I am told is that the line intersects the circle at 2 distinct points. Look at this equation. Isn't this an equation that tells me the x coordinates of the points where they intersect? Because that's how I set these simultaneous equations up, right? So here's the thing. If I know that there are 2 points which they intersect, I must know that this equation has 2 solutions, right? So there are 2 distinct x values because there's 2 distinct x coordinates where they intersect. Therefore, this thing here must have a discriminant which is greater than 0, okay? So, this thing is greater than 0, then b, which equals b squared minus 4ac, a is the x squared coefficient, b is the x coefficient, c is the number on the end. I've got an inequality, haven't I? I therefore know that 10k minus 6 squared minus 4ac is greater than 0. Cool. So, work it out, I suppose. So, this thing, I'm going to square this. So, I'm going to get 100k squared. I'm then going to do twice the product of these. So, 10k times minus 6 is minus 60k. Double that. So, minus 120k. And then this squared is 36. Cool. 4 times 9 is... maths, 36, right? So 36 times 1 is minus 36. 36 times k squared is minus 36k squared. And then I got a greater than 0. Okay, well, 36 go, which is nice. I've got 100k squared minus 36k squared. So that's going to be 64k squared. So that's that sorted out. And then I've got this minus 120k here. And I know that this thing must be greater than 0. Whew, okay, so let's basically not be silly. I don't want to just divide by k. I need to think about how to solve quadratic inequalities. There's a bit more going on. What I essentially need first are these things called critical values. So what I tend to do is just write CVs. They are just the values for which this thing would equal 0. So it's like these end values. So if I was solving the equation this thing equals 0, what I would do was I would take a k out, and then separately set each bracket equal to 0. So I would either have k equals 0 or k equals 120 over 64. I think my calculator is going to help me simplify this fraction here. It's 15 over 8. Okay, so the reason I want to get these critical values is because if I was to give a super rough sketch of this thing here, if I was to sketch this, like y equals this, it would hit the x-axis at 0 and 15 over 8. So it would look like, not look like that at all. It would look a bit more like that, okay? 0, 15 over 8. The question then becomes, when is this thing greater than 0? Well, it's all of this stuff over here and all of this stuff over here, is it not? So if this is 15 over 8 and that's 0 there, it's going to be greater than 0 for values of k greater than 15 over 8, or values of k less than 0. Two separate solutions there. Two separate regions that give us two distinct points. Sweet. There's a very, very pedantic point here that you don't really have to worry yourself with, but it's worth talking about for those inquisitive amongst you. But don't worry about this if you're not bothered. Essentially, I said here the bit of logic I used was this line intersects the circle twice. Therefore, there must be 2 points for which there's two different sets of coordinates for where they intersect. Therefore, this equation must have two distinct solutions. But there's a tiny point here, because this is for the x coordinates, right? Imagine I had a circle. Let's draw a circle here. And then I had a line. So generally, you've got a line, it intersects it twice, two different coordinates. What if the line was this, though? If the line was that, yes, we would still have the two distinct points. However, the x coordinate of these points would be the same, right? Would it not? This could be 2, 4, and this could be 2, 10, for example. They're two distinct points, but the x coordinates are the same. So why did I just say, oh, the discriminant has to be greater than 0? Because why didn't I take account of the fact that this could happen? In this case, the discriminant would be equal to 0 because the x value would be a repeated root. The reason is because the line has equation y equals kx. If you were to think of this, the equation of any vertical line is just in the form x equals some constant, isn't it? There would be no way to get the equation y equals kx that would be a vertical line like this. So that's why I said that the discriminant can be greater than 0 there. That's a super, super specific point. If it said the line with equation x equals 4, for example, cuts at two distinct points, then this wouldn't have been the case. But then we wouldn't have had to do all of that because this is an equation for x. We would have just known that the coordinates of the x values are just 4 anyway. So yeah, that's just for those inquisitive amongst you. But otherwise, I think that's done for question 14. Last question. It's easy as that, right? Figure 4 shows a sketch of a part of the curve C with equation, all of that stuff. The point P, which is 4, 6, lies on the curve. The line L is a normal to C at point P. The region R, as shown shaded in figure 4, is bounded by the line L, the curve C, and the line with the equation x equals 2 on the x-axis. A lot of stuff. Show that the area of R is 46. Okay, so it's to show that question. So luckily we can kind of check our answer at the end. Before we're going to have a clue what's going on here, let's get the diagram up. Let's look at R, okay? So what is R made of? Usually with these grim shapes, you can split them up into, there might be a bit of integral, there might be a shape somewhere, etc. If I was to draw a line going down here, that splits this area up pretty nicely, does it not? Because the thing on the left, well, this is kind of like the area under the curve, which we know we can integrate for. And then this thing here is nice because it's just a triangle, isn't it? So I've got a triangle and some integral. If I just split this problem up into two separate things, I basically need to work out the area of the triangle, which we can call 1, and the area of this kind of integral, this area under the curve bit, which we can call 2. We're just laughing, aren't we? So let's do that. Let's call this equation 1, this equation 2, and let's start off with a triangle. Triangles are easy, right? So, triangle, we know that the area is a half base times height. Do we have either of those things? Well, the height of this thing is just going to be whatever the y coordinate of P is. Do we have that? Yes, it's 4, 6. So the height's 6. We know that this here, this x coordinate is 4. So if I only had the x coordinate of this thing here, I would have the width, right? I could have this base. Do I know that? No. Can I work it out? Yes, because I can get the equation of L. If I get the equation of L, I can use that to work out where it hits the x-axis. So let's try and get the equation of L. It is the normal to C at the point P. I always say this, to get the equation of a line, you need two things. You need a gradient and you need a point. Do we have either of those things? We know it goes through P, right? So we have the point already. We know that this x1, y1 is 4, 6. All we need is the gradient now. So what piece of information can I use to get this gradient? I can use the fact that it is a normal to the curve C. A normal to the curve is always perpendicular to the curve at that point. In other words, if I get the gradient of the curve at that point, I can use this kind of rule of perpendicular gradients to get the gradient of the line. Okay, how am I getting the gradient of a curve? I'm differentiating. So if I was to do dy by dx on C to get the gradient function, it would be what? Let's first of all write y, as we've been doing throughout this whole exam, in terms of powers of x. So 32 over x squared is 32x to the minus 2, and then plus 3x minus 8. Okay, now what I'm going to do is I'm going to differentiate. So, bring the power to the front. So it's going to be minus 64, and then, because that's minus 2 times 32, take 1 from the power, so x to the minus 3. 3x differentiates to 3, 8 differentiates to nothing. Okay, we want to find out the value of this function at the point P. So at P, I believe x is equal to minus 4. So I need to find out the gradient function at x equals minus 4. So I'm going to do minus 64. X to the minus 3 is divided by x cubed. So this is going to be divided by 4 cubed plus 3. Now I think this is going to be nice. 4 cubed is actually 64. So this is going to be minus 64 over 64 plus 3. That's going to be minus 1. Add the 3 and I get 2. Cool. So this isn't the gradient of my normal line, is it? This is the gradient of the tangent at that point. The normal is going to be perpendicular. So basically to get a perpendicular gradient, I need to do minus 1 divided by the other gradient. So it's going to be minus a half. So going back to what I want here, I've got my m and I've got my point. If I was to grab this bit here, I can get the equation of this line, because straight away I can go into y minus y1 equals m times x minus x1. We all know I like this. Y equals mx plus c is okay, but I prefer this. So what we're going to do, we're going to do y minus y1 is 6, m minus a half, x minus x1, which is 4. Sick. Okay. Now, yes, I can simplify, blah, 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 but the only real reason I want this is because I want to find out where it hits the x-axis. So why don't I just straight away dish y equals 0, see what happens. So y equals 0 would get me the following. Let's multiply, well, let's first, that's just minus 6, isn't it? Multiply everything by 2. So I'm going to get minus 12 equals minus, and then x minus 4. Okay, it looks like I can cancel a minus sign here. So I'm going to get 12 equals x minus 4. Therefore, x equals 12 plus 4, which is 16. Whoo! I don't even know if we're halfway, to be completely honest with you. It's a bit of a grim one. What we know, though, is that the x coordinate of this is 16. So what is the width of this? This is 4, this is 16, so that's going to be 12. So the height is 6, the width is 12. How are we going to work this out then? So 1, height 6, width 12. I think we're in a good spot then, aren't we? Because if I was to just do a half base times height be half times 6 times 12. Half times 12 is 6, so 6 times 6 is 36. Cool. We're halfway there, maybe. The next thing I need to do is I need to think about this pink area. So this is going to be the area under the curve, which is nice because that's just what integration gets me. So if I was to integrate this curve between the limits of 2 and 4, that's going to sort me out. Okay, so just got to do a definite integral and then we're good. So area 2 is going to be the integral between 2 and 4 of the curve C. So the way I wrote it back then when I was differentiating it is going to be useful here as well. So this is plus 3x minus 8. Home stretch, I'm telling you. So let's integrate. This is a definite integral, so I'm going to be writing my square brackets. Whew. Okay. Add 1 to the power, so I'm going to get an x to the minus 1. Divide by the new power, so divide by minus 1, which is just like making a minus. Plus, add 1 to the power, so that's a 1, add 1 I get x squared. Got the 3, divide by the new power. Minus, constants just turn into x's. These numbers go here. We're getting there. Stick the 4 in here, stick the 2 in there. So I'm going to get minus 32 times 4 to the minus 1 plus 3 over 2. I'm running out of space in my bracket because there's just so much stuff to do. Times 4 squared minus 8 times 4. And then minus, similar thing. So minus 32 times 2 to the minus 1. Plus 3 over 2 times 2 squared minus 8 times 2. Oh, grim. So you can put this into your calculator. I'd just be careful. Sometimes, you know, the more stuff that goes into your calculator, the higher the probability of making a mistake. So maybe I'll just work out like the first bracket first. So this is going to be what? Minus 32 times 4 to the minus 1 plus 3 over 2 times 4 squared minus 8 times 4. That gives me this as minus 16. And then I'm minusing whatever's in here. So now I'm going to do minus 32 times 2 to the minus 1 plus 3 over 2 times 2 squared minus 8 times 2, which gets me minus 26. Look at all these minus signs. Minus 16 minus minus 26 is going to be minus 16 plus 26, which is going to be 10. Therefore, the area of R, which is basically both of these areas added together, I got the first area as 36, the second area as 10. So the area of R is 36 at 10, which is 46, which is the right answer, which rounds off the paper very, very nicely. That was quite quick, so maybe I can get paper 2 recorded today. Let's see how it goes. Best of luck with it.